sonar, biomimetic sonar, and in particular how you can use such a biomimetic sonar system to do biomimetic navigation or map building. My name is Herbert Peremans. Jan Steckel is the PhD student who did all the work. So there's a standard problem in robotics, which is that if you want to have an autonomous system, it must somehow be able to build a map of its environment. And the standard solution to that problem has been to provide such robots with sensor systems. Vision sensors or laser scanners are typical sensor systems, sonar, that provide this information about the environment. But it requires you to, when you read out these sensor data, you have to segment them, you have to interpret them in terms of objects in your environment, because the way these schemes work is that by measuring the relative displacement of the robot with respect to a fixed part of the environment, you can both estimate your own movement and you can start building a map of these parts of the environment. And that's why it's called SLAM, which stands for Simultaneous Localization and Mapping. There's a whole range of such algorithms that have been developed. The problem if you want to use sonar together with those algorithms is that sonar provides you with a very sparse sampling of your environment, and sparse both in terms of measurement rate. 10-20 hertz is about what you'll get, but also in terms of spatial resolution. So you get a few echoes back from some of the objects in the environment, and that's the information you need to use to build this environmental model. So that has stopped most people from using sonar for this particular purpose. What I would like to present today is a different way of performing such SLAM, simultaneous localization and mapping, doing it in a more biologically inspired way, and not use a standard sonar sensor, but use a biomimetic sonar sensor. And the sonar system we've built is, well, it interfaces with a PC. It's a standalone FPGA-based system which contains one channel for emission, so you can provide a particular signal you want to emit, and this is, this is then being sent to this transducer, which is a commercial off-the-shelf Polaroid transducer. The echoes, once you emit sound into the environment, the sound will reflect and get back to you. The echoes are collected by two microphones, which are, again, standard Knowles microphones. But because of their small size, they would be omnidirectional. And if you want to extract information about the shape of your environment, you want some spatial information to be in there. And that's why we fitted those microphones into these two plastic replicas of the outer ears of a particular bat species. In this case, it's, for the biologists among us, Micronycteris microtis. We've scaled up those ears by a factor of 1.5, which allows us to use frequencies that are within the range of this emitter. The signal itself is again inspired by signals used by a particular class of bats. They are called FM bats because they use these frequency modulated chirps. And here you see in this spectrogram how the frequency varies from about 100 kilohertz to 20 kilohertz over a time of 3 milliseconds. And this is a linear period modulation or a hyperbolic frequency modulation, because that's the sound these bats actually use, and there are these calls have particular properties that make them useful to the bats, so that's why we use those as well. this is our biomimetic sonar system. Why do we use these outer ears? As I said, these microphones would be omnidirectional. We want spatial information. Putting microphones into the ear canals of an outer ear shape like that, the sound waves, when they return back to this robotic head, they diffract and interfere with each other, and that gives them a direction-dependent filtering property, which is called in hearing research the head-related transfer function. So we basically construct a spatially dependent filtering. And the next step is mounting this sonar system onto our mobile robot. But with this slide, I first want to show you what happens if you try to localize yourself and you don't use information from your sensors observing the environment. Then you can use the commands that are being sent to the motor system, and you can assume the motor system to be 100% accurate. So you just integrate the path you think you're following, and this nonsense is what comes out of that. So in the end, we'll see if we use the sonar system, we get a much more sensible idea of where we actually been. How do we do that? So we add this sonar head I just described to our mobile robot. The signals being picked up by these two microphones in the ear canals are then being processed by a very simple functional model of what's going on in our inner ear, so in the cochlea, which basically is a set of bandpass filters, each centered on a slightly different frequency, and then the output of those bandpass filters is AM demodulated. That's a very simple model. That's the one we use, and that gives us this kind of information. So what you see here is the spectrogram from the right and the left ear, well, one on top of the other. The blue means you're not getting much echo energy back. It goes to red for the stronger echoes. You can also see the frequency modulation, which is still in there over time. That is the fingerprint or the signature for the particular position this robot was in when this measurement was collected. This is the environment information we're going to put into our navigation system. The navigation system itself is based on a thing called RatSLAM, which was developed by these two people, and is basically a model of what's going on in the mammalian hippocampus, where there's plenty of experiments that have been done in the meantime on different mammals, but most of this work has been done originally on rats. That's why it's called RatSLAM. And there you have a network consisting of so-called place cells, and whenever the rat is at a particular position in its environment with a particular orientation, this particular cell will fire. So basically the cell is a marker for the state the rat is in. This is what this place cell model duplicates. It's a functional model of that mechanism. So the one source of information is, of course, what the motor system tells the rat it's actually been doing. So there is this path integration component in there providing information to these place cells, but that can't be enough, as we've seen with the results coming out of that. So added to that is this environmental information, and this is being modeled just by a database of templates. This acoustic signature of the environment, of the state of the robot at a particular point in the environment, is being stored in a database, and whenever a new measurement is collected, it's being compared to all these stored templates, and if nothing is recognized, it's assumed to be a new position. Whenever it is sufficiently similar with the template which is already in this database, there is a corrective signal being sent to this place cell, which then allows the robot to combine its own estimate of where it is with what it would expect to see if it is at that particular position. It's already been before, and that then allows you to update your own state estimate, and makes it possible to build a consistent map of your environment. I should add that basically you're building a map of your path through the environment, not so much a map of the environment itself. This is the system. It actually works, and I have a video to prove it. But last part, if I've got time left. So this scheme works by storing fingerprints of positions in the environment. What you see here are two different fingerprints collected from these places marked by the red dots. The black ones give you all the other positions in the environment where this particular template was also recognized. So they tell you how much ambiguity there is in this particular fingerprint we've chosen to model the environment. And some of these are very unambiguous. You only get this type of fingerprint in these two positions. Others are a lot more ambiguous. And to get a better idea of what fingerprints are sufficiently unambiguous to be used to get a good localization of the robot, we've done a second experiment where we ran the robot through a much smaller environment in this square-like path a couple of times. We tracked its actual position, so we know where it was, and we divided that in 78 positions, which means that each of those positions can be coded with about 6.3 bits of information. And then we tried two different schemes, so the fingerprint scheme I've been talking to you about, and then a much simpler one which resembles much more the current type of sonar sensors, where you have a range energy profile. So the amount of energy being reflected from a particular distance is the only information you have about the environment. And we want to see which of those two is most informative and whether we can find a good measure to express in a quantitative manner how informative these two are. And for that we went back to information theory, and we calculate, based on the experimental data we collected, we calculate the probability distribution given a particular measurement that you are in one of those 78 positions. And I show them here for all 300 positions this experiment consisted of, well, for all 300 measurements this experiment consisted of, and these are the 78 positions the robot could be at. And so in an ideal world I would see a single band of dots going along these diagonals, because every time the robot would think it was in the correct position, and no other position would have a probability different from 0. As you can see, there is a difference between the binaural scheme and the range energy profile. The binaural scheme is a bit cleaner, it has less ambiguity, but looking at these probability distributions, it's not that obvious. And for that, to make it more obvious, we calculate the entropy in each of those probability distributions, the amount of ambiguity or uncertainty, and average that out over all measurements that can be collected from a particular position. And that gives us this average entropy, which is visually shown here. So black is good. It means you have 0 bits of entropy, no ambiguity. White is bad. It would mean that well, it wouldn't be that bad. It would mean that you lose 2 bits of information. You would still have 4.3 bits of information about your actual position. But anyway, this scheme, we think, allows us to have a quantitative comparison between these 2 different signature-producing methods. That summarizes my talk, but it also finishes off my time, I guess. Okay. For those of you interested, I've got a little video I can show you where you see this scheme working.